So what I'm basically going to present is an overview of layer 2 protocols, and it's going to take about an hour to an hour and a half, or sorry, an hour and a half to 2 hours. So I'm hoping to cover our payment channels, routing on these networks quite briefly, why payment channel hubs are really awkward, and also why commit chains and rollups are really exciting. So before I begin, has anyone here tried to use the Lightning Network? Has anyone tried to use like a Lightning wallet? We got one person, that's awesome. Cool, and how did you guys find that experience? Just, I don't know if you guys want to yell out. Okay.
A year ago it was difficult, but now it's getting really quite simple and user-friendly.
Okay, cool. Are you using Blue Wallet now, or using Eclair, or?
Blue, Eclair, Phoenix.
Awesome. I want to try Phoenix, actually. Phoenix is on my to-do list.
Phoenix is great.
I mean, the promo looked really good, yeah.
Highly recommend it.
How is Phoenix better?
How is it better? It abstracts you away from a lot of the complexity. So they do a lot of the channel management and stuff for you, which basically means that you just have one balance where you can deposit and withdraw. And it's very simple, very straightforward. Cool.
Awesome, yeah. Yeah, and the channel management is actually very tricky. So that's really exciting. So the whole point of me mentioning that is that layer 2 is alive on Bitcoin, for at least. It's been around for a year or two, and now you can go play with it and try it out. Now that's the channel aspect, and I'm going to talk about channels in depth and sort of the long history of getting to where we are today. You know, it's very easy in 2020 to look at the Lightning Network and think, wow, that's awesome. You know, that must be so easy to build, when it's taken about 7 years from the original idea to deployment. And then on the Ethereum side, and this could also be applied to EOS and other blockchains, there's this concept of a commit chain or a rollup. We have a central operator. Their job is to create blocks and post blocks to the blockchain periodically, like little block hashes. So the idea there is that in Lightning, there's collateral lockup for a hub. You have to deposit coins that facilitate your users. And on commit chains, there's no collateral lockup whatsoever. Anyone here could someday be a commit chain operator. So right now they're like really jargon, techy, boring words. But by the end of it, hopefully you'll appreciate why that's significant. So before I also begin, who's heard of Plasma or rollup before? A few people, okay, cool. So we're going to cover all of that today. What I should also mention is that I work for a company called Pisa. We're building some of this, but it's not really our main focus at the moment. This has been my general interest for about 6 to 7 years. So that's mostly why I talk about it. Cool. So what's the motivation for these off-chain protocols? So when people normally talk about off-chain protocols, they always think about scalability. You know, you have Bitcoin and Ethereum. They can support on the magnitude of 10 transactions per second. And that's because we're sending a transaction out that needs to be processed by the entire network. Thus, a good way to scale is instead of sending every transaction to the network, why does Alice and Bob not just send the transaction back and forth between themselves? You know, if they send it locally, you don't interact with the network, so you should scale much better. But actually, there's a much better way to motivate this problem. So I've got 3 slides, and by the end of it, you'll think off-chain is a no-brainer. Or I hope so anyway. So who's ever deposited coins into an exchange or an online service? Everyone here, look at this, the hodlers. Cool. And I assume it's a custodial exchange. You go on the exchange, you deposit your coins, you trade back and forth thousands of times. You go offline, the exchange gets hacked, and they lose all of your money. You know, that's the typical story around this. So by 2016, according to Goon, 33% of exchanges had been hacked. And when they get hacked, they're large-scale thefts. You know, Mt. Gox loss of the magnitude of 850,000 Bitcoin. 2016, Bitfinex lost 120,000 Bitcoin, etc., etc. Every couple of weeks, an exchange will get hacked. So the real motivation for these off-chain protocols is, can we keep that same user experience? Can I log on to an exchange or an online service? Can I perform my trades on their website without having to trust that exchange? Can I still have self-custody of my funds? So if they do get hacked, they don't lose my coins. Maybe some of the trades get censored, but I still have control of my money and I can just withdraw it. And that's the ultimate goal for off-chain protocols. So everyone here's already had that off-chain experience. It's just been completely custodial. And that sort of sucks. Yep, go ahead.
Isn't that being done on fully decentralized exchanges?
So DEXs are a way to achieve that. Yeah, exactly. But most DEXs today tend to be on-chain. So that's like Uniswap or even the Binance DEX. So they're going to hit a throughput limitation at some point. So for Uniswap, for example, there's a smart contract on Ethereum, but that means they have to hit the Ethereum throughput limit, which is like 10, 15, 20 transactions per second. Binance are creating their entire blockchain just to run a DEX, but their limitations again going to be how many transactions can I get sent to the network. Where in this case, what I care more about is as a central operator, what if I only have to process the transactions and we don't have this global network? But we do it in a way where you don't have to trust me. So that's the ultimate goal. So this is sort of the layout for the talk today. First, I'm going to talk about channel-based networks and the long road towards the Lightning Network. Then afterwards, I'll talk about commit chains, payment channel hubs, and also some of the rollups. And by the way, if you have any questions whatsoever, please ask. Raise your hand, yell at me, just get my attention and ask the question. This is more of a workshop and a learning experience than it is me just talking for 2 hours. Because, yeah, I would get bored listening to me for 2 hours. Cool. And of course, you always have this standard scalability slide. Why is off-chain exciting? I mentioned it's exciting because you can build these self-custody exchanges, which is something that's hopefully the ultimate goal for cryptocurrencies, but also just for scalability. If we can take all of the transactions off-chain, then you could actually achieve, I always put this bullish number up, 100K transactions per second. And why is that? Because 99% of transactions are local between the parties and not the global network. So you bypass the blockchain latency, you bypass network fees. If Alice and Bob are sending the coins back and forth, there's no fee for that. But of course, we want to achieve this in a way where we don't have to trust anyone. I don't have to trust the counterparty. Cool. So let's talk about off-chain channels for a second. So we have Alice and Bob, and they want to open a channel together, and they want to send coins back and forth. What they're going to do is they're going to lock up coins in a channel. So there'll be an on-chain transaction where the coins are locked in for Alice and Bob's transaction. And typically, there's some off-chain progression or off-chain transfers. So what would this look like? So what you can imagine is that Alice has locked up one coin. And I've got it here. She's locked up this one coin. Now what she's going to do is send the coin to Bob. So he'll send a message and she'll say, Bob, you're now the owner of this coin. And now Bob has the coin. Now what Bob's going to do is maybe Bob wants to send the coin back to Alice. He'll sign it and pass it over to Alice. And they can do this hundreds of times back and forth. And really all they're doing is redistributing that initial deposit. There's one coin in a black box, and then there's this list, and they're saying Alice is the owner, Bob is the owner, Alice is the owner. And that's how off-chain works for channels at a very high level. They're just reassigning ownership of that coin. And of course, you can extend this to general smart contracts. So instead of a payment, that could be a game. It could be rock, paper, scissors, it could even be e-voting or some casino game. But for now, we're just going to consider payments. But then the big question is, what if Bob goes offline? Alice and Bob have been transacting back and forth. Alice is the current owner of the coin, and then Bob goes offline. Does that mean her one coin is stuck and she can't get it out of the channel? If that was the case, it wouldn't be a great scenario. So what we actually introduce is this idea of a dispute process. Okay? So what Alice can do is Alice can send evidence to the blockchain. And she can say, blockchain, here's evidence that I own the one coin. And this will trigger a dispute process, this fixed period of time for Bob to respond. Bob could provide evidence where he could prove, well, Alice did own the one coin, but then she transferred it to me, and now I'm the owner of the one coin. So it's a bit like a court. Alice will send evidence, and Bob will send evidence, and they have a time window to do that. And then, yep, go ahead.
Is the dispute period set up as a timestamp or as a block height?
Oh, you mean for the dispute process, or the?
So, as I understand it, it says that if no value has been exchanged, if no value has been exchanged between this time, the time the channel has been created, and
Yep.
this time, it does when use time is set up as a, like a timestamp.
Okay.
It's set up as a, like a block number. Like
Yeah, there's different ways.
5,000.
Yeah, so there's different ways you could do it. You can do it based on block height, or you could do it based on a global clock. Block height's a bit easier to deal with because that's the native time to the blockchain, where most blockchains don't really have a. They have a loose range on current time, so they can't get it to the second. Blockchain's time can be Bitcoin's time can be out by like 2 hours, where Ethereum tends to be, I think, 5 minutes. Let's say it's much smaller, but they don't have an exact, definition of time. It's very loose, so block height tends to be used. So for this fixed dispute period, what you can imagine is that Alice would say, blockchain, I want to close the channel. Here's my evidence. Trigger the dispute process. And now Bob has to respond within 100 blocks or 1,000 blocks. If he doesn't respond, then the dispute process will conclude and resolve. And of course, what will happen here is that Alice will be able to withdraw her coin. The blockchain will see, well, Alice's evidence is correct. Bob tried to cheat. Either he didn't respond or he just didn't, give me recent evidence that he owns it. So surely Alice should get the coin. So the blockchain becomes this arbitrator, this settlement system. It's no longer used to process every transaction. It's just used to open channels and to resolve disputes, given the evidence that is received. Okay, so that's like a different way to think about using a blockchain. It's more to do with off-chain interaction and using the blockchain at, using the blockchain, what's the best phrase for that? As little as possible, or in the worst case scenario. Okay? So that's a high level view of how these channels work. So now what we're going to do is deep dive into some of the technical details of how we've got here. And there's different ways we can build these channels. We have Spearman channels, Duplex channels, Lightning channels, write-in channels. You have a bunch of different ways to do state channels. So what we're going to do is go through the payment channels for at least Bitcoin one by one. So this includes Spearman channels, which we call replaced by incentive. Duplex micropayment channels called replaced by time lock. And then Lightning, how it's implemented today, is replaced by revocation. So there's different ways where you can update the state of a channel. So let's consider it one by one. Spearman, Spearman one-way payment channels. So this was originally invented in 2013 by Spearman, but actually historically there was a post by a guy called Hashcoin. That's how this field works. Everyone has a silly name. Hashcoin wrote a post in 2011 that described the same idea. So while most people accredit Spearman, there's actually a guy called Hashcoin that invented it in 2011. So that's 9 years ago now. So how does this work? So these Spearman channels can only support one-way payments. Alice to Bob, but not Bob to Alice. So Alice will deposit one coin. And this coin can be redeemed if one of the following two conditions are satisfied. Alice can be refunded after time t. So Alice will lock up the coins. There's no activity whatsoever. So then after time t, which could be a block height or real world time, she could then withdraw her money from the funds. So she's always guaranteed a refund. Or if Alice and Bob cooperate, they can redeem the coins immediately. They can immediately close the channel and send the coins either direction. Very simple conditions. So that's basically what the funding transaction would look like. Alice is put in coins, there's two scripts that could be satisfied, and there's one coin in the channel. Now Alice will broadcast this to the network and it will get accepted to the blockchain. So now it's all set up and Alice can start paying Bob off chain. So how do we authorize these payments? Well, what Alice is going to do is she'll create a new transaction called the payment transaction. And she's going to send Bob 0.1 Bitcoin. So in this transaction, Alice will receive 0.9 Bitcoin and Bob's going to receive 0.1 Bitcoin. She'll sign this and give it to Bob. And now Bob can make one of two decisions. Bob could sign this, broadcast it to the network immediately, and redeem his 0.1 Bitcoin. Or he can just keep it secret. he's aware that Alice isn't going to get refunded until time t. So this channel could be open for 10 hours or 2 weeks. So he doesn't have to broadcast this right away. So he just keeps it secret. Okay? And now, the new balance of the channel is that Alice has 0.9 Bitcoin and Bob has 0.1 Bitcoin. So how do we do another payment? Well, it's really straightforward. Alice will authorize a second transaction, payment transaction 2. And now she's going to send Bob 0.2 Bitcoin. So he'll sign it and give this to Bob. Now, of course, in this transaction, Alice will get 0.7 Bitcoin back, and Bob's going to get 0.3 Bitcoin. And now, of course, Bob can make the same decision. He can say, well, I'm just going to keep this secret. Now, what does Bob do with the old transaction? In fact, let me remove that. What do you guys think he's going to do? So we have 2 transactions, payment transaction 1, payment transaction 2. What do you think Bob's going to do with payment transaction 1?
He'll just keep the second transaction.
Exactly. He'll just keep it. He can say, well, transaction 2 is always going to pay me more money. So why would I keep payment transaction 1 around? So he can just discard that. All he cares about is keeping the latest transaction that will pay him the most coins. And that's exactly why we call this replace by incentive. Bob has the incentive to keep the latest state, or the latest transaction, that will pay him the most money. And that's exactly how we guarantee the latest state is sent to the blockchain. The evidence of the latest evidence agreed. So blocks are ticking away, there's no activity, and eventually Bob can broadcast that and claim his new Bitcoins at any time. And of course he should do that before the refund, before Alice can get her money out. And of course the worst case scenario, if there's no activity, Alice is always refunded by time t. So her coins are never at risk for opening this channel. So that's the easiest payment channel that can open.
Do you keep the latest transaction or the highest transaction?
For Bob, he would always keep the one paying him the most money. So this is only a one-way, so this channel can only do one-way payments.
Okay.
We'll get the
highest.
Yeah.
Yeah.
Yeah, just keep the highest. I don't want to refund you, so, Go ahead.
I'm not sure to understand what happened to transaction 1 then.
It just gets discarded. So it's kept off chain. So if you think about like database-wise, every time you pay me, I add it to my database. But now my database is getting full of payments. Then I have to make the decision, do I need to keep all of these? And really I just need the latest one that will pay me the most money. So I just discard all the previous transactions.
So Alice is not charged for the lowest transaction that she...
Yep, this is just like local between you and I. We just share these over, Messenger, WhatsApp, whatever. So we never talk to Bitcoin.
Transaction was replaced.
Yep, it's replaced. Yeah, exactly. Replaced by incentive. Cool. Any other questions at this point, by the way?
So can there be more than 2 participants?
There can be. So normally for channels, you need to have everyone agree to every new payment. So in this case, Alice and Bob are agreeing, but Bob's decision comes later. If you have 3 payments, and that is doable, you need all 3 parties to agree to every payment. Just because if you had 2 people agreed, you could cheat the third person.
Who is choosing the latest transaction then?
If it's a multi-party, it'll be whoever's doing the payment. So maybe I want to pay you, so I propose this new transaction, and then we all agree to it. Yeah, and then there should be a local timeout, and then I just close the channel if you guys don't respond to me. Yeah, but people just tend to do 2 channels. Once you get up to like 5, 6, 7, large channels, it becomes more, what if one user goes offline? They go offline, you have to close the channel. So it becomes like a really bad user experience. Yeah?
So if that's the case, why wouldn't individuals just opt for permission blockchain or private blockchain?
You'll see why. Let's get to the end of this first. But yeah, obviously, well, I guess one reason is that in the permission blockchain world, you have to trust the federation, where here you're really just trusting miners. You have to be financially invested. That's why they tend to go for the cryptocurrency world. But these techniques could also be used on permission blockchains. So one permission blockchain that's quite popular in Bitcoin is called Liquid by Blockstream, and that has a federation that runs the blockchain. So it is a permission blockchain, and they have Lightning Network support now. So you can run it there as well. It's not restricted to cryptocurrencies. Cool. So what if we want to support bidirectional payments? I've sent all these coins to Bob. Why can't Bob send the coins back to me? So my disclaimer is that the following bunch of slides may hurt your head a bit. But don't worry if it hurts your head. This is more of a historical fact, and you should really never build a payment channel like this. If you build it like this, please don't say you ever attended this lecture. It meant I failed. Cool. So one other technique is called replace by time lock. And this is around 2014, let's say. So every time we change payment direction, we're going to reduce the channel's expiry time. Okay? So let's just have a good example. So now the transaction set up again, where Alice will get refunded on or after block 20. Otherwise, if Alice and Bob agree, they can redeem the coins immediately. So this is basically very similar to how we set up the previous one. Alice is always guaranteed a refund after block 20. And if Alice and Bob cooperate, they can close this channel immediately. Cool. See, refund is valid then. So Alice is going to send coins to Bob again. But now there's a slight difference. This transaction has an expiry time of block, T19. I wrote days there, but it could be blocks. So Bob can only redeem this payment on block 19 or afterwards. He can't redeem it immediately. Okay, so there's a slight difference there compared to the previous example. Now what's nice is that Alice can keep paying Bob this one direction, and that time never changes. This transaction can always be redeemed at block 19. Okay, so the new payment is still valid then. Now let's change payment direction. Now Bob wants to start paying Alice. How do we do that? Well, Bob's going to authorize a transaction to Alice, and he's going to reduce that lock time. So now Alice's transaction can be redeemed at block 18. Okay? So as you can see here, and I'll just walk over to this, okay? Alice's transaction can be redeemed on this block, but if she isn't fast enough, Bob could reverse the payment by broadcasting his payment here. And of course, if Bob isn't fast enough, Alice is eventually refunded here. So if you notice what's going on is that the latest state of the channel is enforced by when that latest payment expires. Now what's really annoying is that if we did 20 payments back and forth, that expiry time would be 0. And the channel would have to be closed immediately. So who would ever want to implement that? Raise your hand if you think that's a good protocol. No one. Cool. Just wait till you see the next one. Oh. But that's important. This is a really awkward thing to build. Reducing these lock times for every time you change payment direction. And you need this safety time gap between the two payments. Okay. Now let's talk about duplex micropayment channels. So the author of this paper, C. Decker, he looked at how Spielman channels work, how replace by time lock works, and he thought, why don't we combine both? If I can combine both, maybe we get the best of both worlds. And we can alleviate that problem of the time lock being reduced. And again, please never implement this protocol. Okay, you'll see why in a second. So this protocol has two components. One is a pair of one-way payment channels. So Alice has a one-way payment channel to Bob, and Bob has a one-way payment channel to Alice. So now there's two channels, for bidirectional payments. Now, whenever one of these channels exhausts their resources, so Alice has sent all the coins to Bob, maybe a better way to explain it is, I have a board, don't I? But I bet I don't have markers. Kings never has markers. Okay, I don't think it has markers. Cool. But what you could imagine is that Alice has one coin in a channel with Bob. And Bob has one coin in a channel with Alice. Now Alice has sent all of her coins to Bob. And Bob has sent all of his coins to Alice. Now if you have two one-way channels, Alice can't send any more coins to Bob. She's already sent that full coin. And Bob has his one-way payment channel with Alice. And he sent the full coin. So they can't send each other any more money. But they both have one coin each. So what you want to do is destroy that channel and recreate them and refill the coins that you can send. And that's what this invalidation tree is going to do. Okay, so it's going to look a bit like this. So Alice will send the coins to Bob, and Bob will do the same to Alice. And as I mentioned, they'll both run out of coins that they can send. So clearly here, Alice can no longer send coins to Bob, and Bob can no longer send coins to Alice. But they both have 1 coin each in terms of their final balance. So the idea is to destroy those channels and recreate them in an off-chain manner. Okay, so is there any questions at this point before I continue? Is everyone with me?
Can you repeat it like?
Yeah. So cool. So these are 2 one-way payment channels. So Alice has deposited 1 coin into a channel with Bob. And the payments can only go in one direction, Alice to Bob. Then you have another payment channel from Bob to Alice. And Bob has put 1 coin into this channel. Okay? So you're like Bob and I'm Alice. Okay? So I keep paying you in my channel. So I keep paying you here and you eventually get 1 coin. And then you keep paying me back. You keep sending me your coins until I get all the coins here. So now you have a coin and I have a coin because we received them here. But we can't send any more coins because my one-way payment channel here is exhausted. Does that make sense? Cool. Any other questions? Or is everyone sort of happy? Cool. So now the question is, can we destroy these channels and recreate the channels in an off-chain manner where we refill the coins that can be sent? You know, it's a bit like getting an hourglass and turning it upside down. You refill it so it keeps going down again. Cool. So what he proposed is his invalidation tree. But I'll go over this one first. Yeah, it's a bit crazy. So there's a funding transaction and there's 3 intermediary transactions. And they all have this lock time. So this branch can be broadcast to the blockchain, let's say on block 100. That's exactly the time this can be broadcast. And at the leaves are 2 one-way payment channels. Now when you run out of coins there, what do? You destroy the branch, or you replace it with a new branch and a new pair of one-way channels. So this, you reduce the lock time here to 99 days, then they can have 100 days each with a pair of one-way channels. And when you run out of coins again, you just keep repeating this process. So you have this invalidation branch, or this invalidation tree. Now again, who would want to implement this protocol? Raise your hand. Who thinks they could implement this now after me explaining it? Exactly. That's why it's so complicated. So please never implement that. But that's really important. So this is now 2014 for the Lightning Network. This is the best protocol that we have. And everything looks very clunky. It's hard to get rid of the expiry times. It's hard to get rid of limits on the throughput of channels. And what's really nice is that the Lightning channels by Joseph Poon and Taj, it fixed this problem. So how did it fix it? It fixed it with this idea called replace by revocation. And this is basically what's implemented today on the Lightning Network. So we have Alice and we have Bob. And each party has a transaction or a state that only they can broadcast. So Alice's state represents, Alice's balance and Bob's balance. And Bob has a similar transaction that'll say his balance and Alice's balance. So they're symmetrical. They basically have the same information, but Alice has a transaction that only she can broadcast, and Bob has a transaction that only he can broadcast. Okay? Very simple so far. So when you authorize a payment, it's a 2-step process. They're going to exchange a new pair of transactions, the latest state of the channel that represents their new balance. So if I'm sending coins to Bob, the new transaction is going to say that I get X coins and Bob's going to get Y coins. Okay? So every transaction just has both, balances. And then what we do is we have to revoke the old pair of transactions that represented the old balance of the channels. Okay, so what we're going to do is share secrets that will revoke the old pair of transactions. complete. And now we can keep doing this. So what you end up with is a set of transactions that should never be broadcast to the network, because they represent old balances and old states. And you have one transaction that should be broadcast to the network to close the channel. Okay? So is that clear so far, as a high level what's going on? Every time we do, yep.
What happens if you send it at the same time?
At the same time, so it's more like a two-phase commit. So what's important is that you need to make sure that you've received, Bob is authorized the latest state, and Alice is authorized the latest state. So I send you my signature, you send me your signature, and now I'm guaranteed I can always broadcast the latest state. And I'm guaranteed that you can always broadcast the latest state. So once I'm confident that I can close the channel with the latest state, then I can revoke it. So it's like a two-phase commit. We agree, and then we perform.
So if someone broadcasts an old state, it's going to get rejected.
Well, that's the thing. So yeah, this is why it's replaced by revocation. So what's important is that every revoked state, they're valid transactions. And they can always be broadcast to the network at any time. So then the question is, what does it mean for this to be invalid? Okay? So this is basically your question. What if Alice goes offline and Bob tries to broadcast a revoked state? So maybe Bob has sent you all the coins. You go offline to go buy a Lambo, because that's what we do with Bitcoin. And while you're trying to buy your Lambo and trying to convince them you have coins in a Lightning channel, Bob's going to try to reverse that payment. Try to broadcast a revoked state where he tries to convince the blockchain he still has his money. So that's the dispute process that we mentioned before. And because you're offline, you can't respond. So that's what Bob would do. He'll broadcast that revoked state. And now we have this on-chain dispute process where Alice has to respond by block 100. If she doesn't, then Bob's going to get all the coins. So, blocks are getting minted, no response from Alice yet. But the question is, what if Alice was online? What would Alice actually broadcast? How can Alice convince the blockchain that this was indeed a revoked state and Bob never had the authority to broadcast it? She'll broadcast a justice transaction, or in the code it's called a penalty transaction, but I prefer justice because it's more fun. So the idea is that if she broadcasts this justice transaction, she can prove to the blockchain that this was indeed revoked. And if she can prove that, then 1, she proves that it's revoked, and 2, she'll penalize Bob and she'll receive all coins in the channel. Okay? Yep.
Is that any case, that might be silly, but is there any case that Bob can actually DDoS Alice?
Oh, of course, I mean...
So she can actually do that step?
Yeah, I mean, one argument may be that if you're running this on a Raspberry Pi, maybe Bob's as DOS as your Raspberry Pi and then you get knocked offline. Yeah, so Alice has to remain online. So you shouldn't crash. Yeah, but we'll get to that, the liveness problem. That's one big underlying issue of all these protocols. But yeah, you're right. You could probably DOS the other person. So, okay. So, any other questions?
What distinguishes this justice transaction?
I'm going to get to that now. I'll get to that. Any other questions just for the idea so far?
What if Bob loses his states? His hard drive goes down.
Yeah, that's another issue. So we'll get to that. Yeah, it'll become obvious in a second why that could be an issue. Any other questions? Cool. Okay, so what you'll do is broadcast a justice transaction. So convince the blockchain that it was indeed revoked. She'll get all of Bob's coins. She'll issue that penalty, and she's really excited. She's a bit embarrassed. She gets her Lambo, and she gets her coins, and Bob's just angry. Now, can Alice just keep around a pre-signed justice transaction? Now, this is where we start running into the issues with Bitcoin itself. So what's annoying is that a justice transaction is unique to a specific transaction, to a specific revocation. It's specific to a state. So every time Alice and Bob do a payment, there's a unique justice transaction that could be signed and broadcast at any time. Okay? So if you do 1,000 payments, there's potentially, well, there's 1,000 unique justice transactions. Now for Alice, that's not a problem, because Alice keeps around enough information where she can detect the breach, she can compute the justice transaction in real time, so you can sign it and broadcast it out. Now this will become a problem, and I don't have a problem here yet. So this will become a problem if you want to outsource this to someone else. So what you could do is hire a watchtower, where you give the watchtower the justice transaction. So if you're offline and Bob tries to cheat, the watchtower can always broadcast that in your behalf. So they can protect you while you're offline. But because of Bitcoin, the watchtower needs a justice transaction, one of these, for every single payment in the channel. So it's order and storage, which you imagine blows out quite quickly. But we'll get to that, or sort of why that is the case. Okay, so now we're going to go a bit deeper. So under the hood, what does this all look like for a Bitcoin transaction? So we have the funding transaction that's off where one coin is locked in, and it can only be spent if Alice and Bob agree. And maybe I should walk over here as well. Okay, so there's one coin locked in, and Alice and Bob must cooperate to release the coin, just like we did before. Now there's two transactions. There's a transaction that only Alice can broadcast, and there's a transaction that only Bob can broadcast. Now they're both symmetrical, so I only have one displayed on the screen. So let's look at Bob's transaction. Okay, so this has been signed by Alice. So Bob could sign it and broadcast this to the network immediately. Now there's an output that will represent Bob's balance, and I think that's the next slide. And there's an output that represents Alice's balance. Now if Bob will broadcast this to the network, Bob has to wait until time t to get his 0.5 Bitcoin. So if Bob tries to close the channel, he has to broadcast this. He may have to wait 2 weeks or a day, and then he can redeem his 0.5 Bitcoin. So that's how we create that dispute process. And Alice can redeem her coins immediately, because Bob broadcast this. Alice can just get her coins immediately. So what's important here is that for Bob's output, Bob can either redeem the coin before time t, so after 2 weeks, or if Alice can reveal a secret S, the pre-image of a hash, if Alice can prove this is revoked by revealing this secret, Alice can claim the coins immediately. And that's exactly how we implement the dispute process. There's one output with two spending conditions. Bob gets the coin after time t, or if Alice reveals a secret, she can get the coins immediately. Are there any questions for this part? Cool. And the justice transaction looks like that. Alice reveals the secret S. She convinces the blockchain that Bob cheated because she shouldn't know the secret, and she gets the full 1 Bitcoin. Okay? So that's basically how Lightning works in a nutshell. I don't know if they're using hashes actually, quite.
Is it Bob that sets the secret? Or?
Yep, so every time we do a payment, I give you a hash, and you give me a hash. And then when we do the revocation, we want to revoke it, I give you the secret, and you give me the secret. So there's a unique secret for every transaction. Any other questions? Okay, cool. So my question is, again, who would want to build that protocol? Anyone want to build this protocol? It's quite complicated. Okay, you're like, yeah, I have a game at it. I go for it. But this is important. That's actually quite a complicated protocol. There's a lot of moving parts. So this was proposed in 2015, and eventually got deployed in around 2017, 2018. Because building this is a lot of work. But the question is this the best that we can do? Is this the simplest protocol that we could implement? And obviously I'm going to say no, it's not. So what's annoying is that every time we fix an issue, we get bidirectional payments, we remove the throughput on transactions, we sort of add complexity to the protocol. It gets more complex. Okay, maybe from here to here it got a bit more simple. But you get the point. It's getting harder to implement for everyday developers. So this really comes about because of Bitcoin and the UTXO model. Sometimes it feels like this. it feels like you're constrained, mostly because Satoshi Nakamoto had no idea how to develop this protocol. He had the idea for channels. So in a Bitcoin transaction, there's a sequence number. And he thought that's how you would implement off-chain. And obviously that doesn't really work that well. So Satoshi had no idea how to implement this. He left, and now as engineers with our toolbox, we're looking at the tools that we have available and we're designing these protocols. And that's how we end up with Lightning today. So the question is, can we do better? Can we make this a bit easier? And so this really first came up in Ethereum on how to do this. And it's really, really, really simple. It's called replace by version. So every time Alice and Bob do a payment, you increment a counter. You know, so payment 1, payment 2, payment 3, payment 4. And then when you trigger a dispute, so it's here, you know, signature by both parties, the counter, and whatever the balance is. So that dispute process just says, trigger dispute, whatever agreed balance has the largest counter is considered the latest state of the payment, you know, the channel. And that's it. So if you do 1,000 payments, I will be 1,000. It's the largest counter, so it's always considered the latest state. Okay, so that's the basic idea there. So you trigger a dispute, you know, you send in I can send in I plus 1. The blockchain will say, well, this counter beats that counter. That's the latest balance. So it's very, very straightforward to do. And what's really cool about this is that, again, there's no expiry time, no transaction throughput limitation. You know, we don't sign transactions per se. It's easy for watchtowers, and there's no clunkiness. So my question here is, who would want to implement this protocol? No one. Oh, one person. Okay, we got 2 hands now. We went from, like, I don't know, 30 to 2. Any other hands? Cool. Okay, there's another one. So this is obviously much easier to do. Now, this isn't new for the Bitcoin community either. And there's real attempts to get this style of dispute process in the Bitcoin. So I stole this slide from Rosbeef. He presented it at BPS 2018. And what you're going to notice is this little part of the slide. You have a state number, you have some random factor, and we just assign the latest counter. So there's, for the past 2 years, they've been trying to advocate replace by version for Bitcoin. And the protocol is called L2. And they also wrote a paper. Who's heard of L2, by the way? Has anyone heard of L2? Okay, cool. That's the Bitcoin side then. You've all heard of L2. And again, here's the basic idea. You set it up. Every transaction has a counter. You have this dispute process. Whatever has the largest counter gets in, and then you pay out. So they want to get this in the Bitcoin because clearly it's much easier to implement. Conceptually, it's much easier to think about. But of course, it relies on a new opcode called Seghash no input. And that's been proposed 5 years ago, and it still isn't in yet. So the purpose of me giving this talk a lot of the time is as the advocate is that if you're ever in charge, or if someone asks you an opinion to say, should we get Seghash no input in the Bitcoin, this is where I say, please say yes.
So
you know,
why it's not included yet?
so in Bitcoin's sort of like, they're all like assembly programmers. That's how I like to think about it. They like to know every single little bit of how the system works. And if you're going to introduce a change to this mission critical system, that change has to have, you know, huge demand and be completely necessary. And not, you know, have many people should not really be against it. So they want to make sure that whatever gets implemented is well engineered and useful. And that's just a very...
Reasonable, right?
A what?
Sounds reasonable.
It is reasonable, but it just takes a very long time.
So the people who are like holding out and saying that they're not in favor of that, why would that be? Why would it be
So Seghash no input can have some, what's the best way to phrase it? It can have some issues if you don't know how it works. This particular opcode has some side effects, let's say. So if you're writing a wallet and you accept Seghash no input transactions, if you don't manage that carefully, you could be vulnerable, I think it's like the replay attacks, where someone could spend some of your coins. So it's quite a dangerous opcode if you don't know how it works. So that's why they're also not very excited to get it in. But we need something in there. There's several ways to do that. You can do it with Seghash no input, there's other opcodes. But it would be quite nice to get something in soon so they can actually implement replace by version.
How does it work, actually?
say cost no input. The idea is that you just sign the outputs of a transaction. And as long as you can make up the coins with whatever inputs, then it gets in. So normally in a Bitcoin transaction, you sign everything.
It's not a specific transaction, it's a kind of, it's the idea of a transaction, and we'll work out how it works later.
Yeah, like here you're basically, so you have an input here, and all you're signing are the outputs. And so you can plug this into this. You know, whatever input satisfies the number of coins that we need, we can plug that in. Yep.
Would the same be useful for being able to, so let's say that we had a three-party multisig, right? Two of three. And you wanted to have any two parties be able to decide to send funds to an indeterminate recipient at some point in the future. Would they be able to use this?
Oh, you can do that right now anyway. So as long as two people sign the transaction, you can send it anywhere you want. This is more to do with...
No, but like,
oh.
so...
Yeah.
You're right. So the example should be either 2 of 2 or 3 of 3. In other words, where one party is willing to agree to allow the other party to send to a as yet undetermined recipient.
I think a better example than that would be you have a program, and you have an input, you have a function, you have an output. Here we're signing the output. You know, whatever the outcome of this program is, that's what we care about. How we get there with the input, you know, what input do we use, we don't care about. So the problem here is that while we sign the output with this in mind, we could end up signing, you know, I sign this and it could be used with one of my other inputs. And then it sends, you know, it sends my coins elsewhere. So it's like a replay attack. But yeah, that's why this has been a controversial change. And I don't think it's going to get in within the next 2 years. But I hope a better proposal comes up than this.
That's a good question.
Yeah.
If you're not signing any of the inputs, what are you sort of authorizing?
You're authorizing that if something can satisfy this program, then you execute it. We know what the output should be. We just don't know what the input is.
But you have no sort of stake in anything if you're not signing any inputs, right? So what are you signing? What do you like?
Well, the idea is that if I can find an input that satisfies it, I just plug them together and put it in, effectively.
Okay, and that other input, do you need another signature for?
That comes down to, I don't think you need another signature for it, from what I remember. So if there's coins on the network that support say cost no input, if there should be a flag, then as long as I get an output that satisfies that, it will clear. But it needs to be enabled, from what I remember. You know, you can look at the specifics though. I haven't looked at the product, like the actual opcode in a year or two, because it's not going to get in soon. But this is important. So one of the things I want to highlight here is that the protocol is very straightforward. You know, we can design this protocol, we abstract a lot of the problems away, and it's something really easy to think about. But as engineers, you then need to think, what tools do I have today to implement that? You know, how can I add another tool to my toolbox in order to make this work? And that's actually what's quite interesting between like academics and protocol designers and engineers. You know, academics ignore all these problems, you know, they ignore the toolbox, where the engineers are like, well, we like this, but we can't implement it. You know, what more tools do we need? This is an observation that I've noticed. Yep.
Does the signing of the transaction, does it impact on the transaction's time?
Time? I don't think it wouldn't impact the time it takes to verify the signature or anything. It's quite standard. Yeah. Yeah, actually, I remember last year I wrote an email with a different proposal. Maybe I can share that with you guys as well at some point. If you guys want to think about different ways to solve this problem. There is a way to solve it without say cost no input. I just don't remember what I wrote. I think I was drunk or something. Go ahead.
So in this protocol, since we only care about the output, is there a lot of I believe there is a lot of security on checking the input, ensuring that
There is right now. So this would relax the security, which is why it's dangerous. Yeah. Maybe after all of this, you know, after we finish the talk, I'll get the opcode up and we can talk about it. We can look at the exact proposal. Okay, cool. Any other questions though about this general idea or? Cool. So if you want to learn, I guess if you want to learn more about like replace by version, I wrote this game about Battleship because I used to attend a lot of these talks in the Ethereum community where they're like, oh, we can play all these games in state channels. And I thought, I don't think that's going to work very well, so I tried it. And it sort of works and it sort of doesn't work. So if you care why it doesn't work, you can read that paper. It took us like 3 months to implement. Okay. Oh yeah, go for it, yeah. I mean, the fundamental problem was that in a payment channel, both parties need to cooperate when they sign every state. Now, what's nice about a payment channel is that there's only one state transition. You know, payment, payment, payment. You could close at any time. If you play Battleship, Battleship has over 200 moves in a game. Okay? So what you could do is Alice and Bob could set up the game, they start playing off chain, and then Bob stops cooperating. If Bob doesn't cooperate, you'd have to close the channel. But what does that mean? If I close the channel, does it stop the game? Well, you can't really stop a game of Battleship halfway through just because someone didn't cooperate. So what you do then is you have to continue the game on the blockchain. And I guess I can pose the question, who'd want to play Battleship on Ethereum if it cost, I think it was $64 and it took 20 hours to complete? Who would play that? No one would. So that's why Battleship didn't work for state channels. It's really frustrating. Okay, cool. But now we've covered the basic idea of channels. And now we all have a rough idea how a Lightning channel works under the hood inside, you know, your little Bitcoin wallet. It's quite amazing that in 2020 they managed to implement that given the tools they have in their toolbox. You know, it is quite incredible engineering. I don't think I'd be able to do it, or at least I wouldn't want to. So now the question is, we have these Lightning channels, but they all only have 2 parties. How do we build a network with this? And we're going to build a network with the humble conditional transfer. Now this protocol is going to look really stupid. You're going to look at this and think, why would anyone ever come up with this for? But hopefully soon we'll see why it's really useful. So we have Alice and Bob. And what Bob's going to do, he gets a secret R, he'll hash it, and he'll send the hash H to Alice. Then Alice will set up this conditional transfer. She'll say, Bob, if you can reveal the secret before time t, you can get this 1 coin. Very simple idea, very simple conditional transfer. Now Bob could reveal the secret and send that to Alice. If they cooperate, they can remove that condition and Bob will get the 1 coin. But what if, you know, what if Alice doesn't cooperate? You know, what if Bob goes over the secret and Alice says, well, I got the secret, I'm not going to give you the 1 coin. Well, what Bob could do is that he has until time t to broadcast that conditional transfer. So he'll broadcast that to the network, he'll reveal the secret, and just like before, the blockchain will say, well, Bob revealed the secret before time t, he deserves the 1 coin. And then the 1 coin is sent to Bob. And that's great. You know, now, again, we're using the blockchain as a settlement system or a judge to make sure that the protocol completes. And that, you know, Bob can redeem the conditional transfer. Hurrah. So what can we do with this humble conditional transfer? There's a very simple idea and it looks a bit stupid. We can build the Lightning Network. And that's exactly what's implemented today in Lightning. They call it hash time lock contracts, HTLC, and it's for path-based payments. So what's really exciting is that Alice can pay Dave via Bob and Caroline in an off-chain manner without trusting any party along that path. And that sounds a bit crazy. In reality, it looks like this. You know, Alice is going to get a coin in her channel and give it to Bob. Bob's going to get a coin in his channel and give this to Caroline. And Caroline's going to get a coin in her channel and give that to Dave. So we need 3 coins to complete this transfer. But at the end of it, Alice has sent 1 coin to Dave. So how do we do this in a way where no one trusts anyone else? Hash time lock contracts. And it's really straightforward. Dave, you know, the receiver, Dave will give a hash to Alice. Now Alice is going to set up a conditional transfer with Bob. She'll say, Bob, if you reveal the secret before time t3, you get the coins, Bob. Bob will then say to Caroline, Caroline, if you can reveal the secret before time t2, you get the coins. And now Caroline will say to Dave, Dave, if you reveal the secret before time t1, you get the coins. So now there's 3 conditional transfers set up. Dave, he knows the secret. He generated the hash. So now we just roll backwards. It's like a two-phase commit again. You know, we set it up and then we complete. So Dave will reveal the secret to Caroline. They both cooperate, they remove that condition, and Dave gets the 1 coin from Caroline. Now Caroline will do the exact same thing to Bob, and Bob will do the exact same thing to Alice. And now they've transferred the coin across the route. Now the question is, what if Caroline doesn't cooperate? You know, what if Dave reveals the secret to Caroline, and Caroline says, well, ha, Dave, I'm not going to give you the coin. And then she takes the coin from Bob. Well, what Dave can do is, before time t1, he can broadcast this to the network, you know, tick it off. The blockchain will say, well, Bob did reveal the secret before time t1, so the blockchain will force Caroline to give the coins over to Dave. And now Caroline has lost her coin. So now she's forced to take the coin from Bob. Okay, so Caroline sends 1 coin to Dave. She now has to finish the protocol. She has to reveal the secret R to Bob in order for her to get her coin back. So that's really cool. It forces everyone to finish the protocol. So that transfer should complete and everyone gets the coins they deserve. Okay, so is there any questions for this part? Or any observations?
Where do we store the route?
Oh, the route's really interesting. So in practice, it's a gossip protocol. So I join the network, I connect to some peers, and they advertise their channels. So when you open the Eclair wallet, and I think I still have it here. Let's hope I still have it here. I have some coins on it. Yeah, so this is my Eclair wallet, and I have a really terrible password. So it's loading. So what normally happens on the Eclair wallet is at the very top if it wants to load. Of course you're not loading. This is the signal's really bad in this room. Okay, cool. So normally up the top left corner, oh, there it is. I don't know if you can see, you probably can't see it on the camera. There's like a little swirl going around. What it's actually doing is downloading the routing table right now. So the active routing table, so then I can find the paths myself. So on Eclair's client side. Sometimes you could outsource it to a server to do it for you.
Also, okay, so you don't have any evidence of the route that your transaction took?
Oh, for this.
Yeah.
We'll get to that. We'll get to the routing bit in a second. I just wanted to show off the Eclair wallet because I think it's pretty cool. Okay, and we can ignore this bit. You know, that's not really that important. But let's consider the good, bad, and the ugly. Okay? So what's good about, you know, these Lightning channels is that there's no real requirement to have a direct channel with everyone else. You know, in this room, I don't need to have like 20 channels, let's say. I really just need 1 or 2 channels, and for everyone else to have 1 or 2 channels. Then I can find a path that connects me to someone else, and then we send the payment across a path. Now, one issue is the free American call option. So a lot of companies and startups, they want to build an exchange on top of Lightning. You know, maybe you give me some Bitcoin, I lock up some ETH, and then we do that transfer over Lightning. The issue is that, and it's exactly this bit here, okay? These coins, so along the path, the coins are locked up for a specific period of time. That could be 1 hour, 2 hours, or 3 hours. So I lock up the trade to Bob on Bitcoin, he locks it up on Ethereum, but now Alice, I guess in this case Dave gets to decide if he wants to finish the trade. So he sets up the trade. Now you can just wait for 3 hours, look at the exchange rate, and then decide, I want to complete or I want to cancel. And he can do that for free. If that route expires, no one has to pay for that. So that's the free American call option. So that's why actually building a DEX on Lightning doesn't really come for free. You know, practically speaking, there's a lot of problems. I mean, if you guys can raise your hand, if you had the option to put a trade on pause for 3 hours, and it didn't cost you any money, would you do it? Raise your hand if you would do it. Look at that, full of traders. Everyone would do it. which is why it doesn't really work that well for trading. But for payments, it works quite well. If there's only one asset on the network. Okay. Another issue is that there's collateral lockup for every hop along the route. So Alice sent 1 coin to Dave, but we needed 3 coins along the path to fulfill that payment. It's quite collateral heavy. But what is cool is that it becomes more like a staking protocol. There's a routing marketplace. If Lightning ever gets popular, I get my little Raspberry Pi or Casa Holo node, I run it at home, I lock into Bitcoin, and now I can just facilitate routing on the network. And I collect a small fee for doing that. So Lightning works best when there's bidirectional payments back and forth. And it's optimistically lightning fast. If everyone cooperates, we can do a payment within, let's say, 2 or 3 seconds. So who's done Lightning? I guess you guys have done Lightning payments. How long did it take you to do your last Lightning payment? Exactly less than a second. It's actually lightning fast. And once it's confirmed, you can always redeem that payment. You don't have to trust anyone for that. But as I'm going to demonstrate, it's not very good for sync payments. So if you're a merchant accepting coins, it doesn't work that well for that. It works best when the coins are going back and forth rapidly. And I have a very good example to highlight that. Okay, so now we have this network of channels. How do we find the paths? Now, what I'm not going to do is go through their path finding algorithm, because 1, I don't really know how the path algorithm works, and 2, we shouldn't really have to know how that works. I think they actually just did a really simple approach. I think they just get the graph, and they just find the shortest path. And really the shortest path isn't what you want. You want the cheapest path. But how do you find the cheapest path? So first, if you are building a routing algorithm for Lightning, what's really nice is that all the channels are public on the blockchain. Because I can see when a channel has been opened. Or at least you should be able to. So all I do is scan the blockchain, and I can find all the channels that have been opened. So I can verify if a channel's opened. And then I connect to this peer-to-peer network. And everyone will gossip about their channels. They'll say, I'm online, and I'm active, and here's my channel. So using the blockchain, I can verify that these channels are really open, and then they can use my service. And actually, I don't know if you guys heard about the recent bug in all the Lightning implementations. The bug was that if I opened a channel with you, or maybe I receive a payment on the network, I never actually checked if it existed on the blockchain. It was never in the build standards, so they've all fixed that bug now. So if I don't verify the channel's open on the network, I could give you a payment, but the channel doesn't exist. It's like a very basic check you should have in the software. But it wasn't part of the build standards, so no one implemented it. I think Rusty discovered that a few months ago. That's how you know this is still reckless. But anyway, the whole point is I can verify channels are open on the network. Yep.
How do you check for open channels in a block?
I mean, so you just look at so you tell me you're in channel ABC or whatever. I look at the blockchain and I say, yep, that looks like a channel.
Okay, so I have to.
I look at the blockchain.
Channel.
Yeah.
You cannot see it in a block, or you don't have any evidence that I opened it.
So the bug was that, I'm pretty sure this was the bug. So if you open a channel with me and then you send me a payment, I should really check that the channel's open on the blockchain. But I didn't check. So you just say, well, I opened this channel with you, Paddy. Here's the payment, and then there's no channel. It was a very, really naive bug. But these systems, the protocol's so complicated that really easy bugs like that just fly by. Because there's so many bigger problems they need to think about. Yeah. Anyway, but that's cool. So one important property is that we can actually derive, the peer-to-peer, all the channel networks from the blockchain. I scan all the channels, then I can build a graph that looks like this, and I can actually see all the connections between all the different channels. And that's really cool. Now, there's some properties you care about. Effectiveness. If I'm running this in my phone, I should really be able to find a path between me and Bob. Whatever routing algorithm you have, it should be effective. And it should be scalable. Right now, I believe there's, 30,000 channels. At some point in the future, there could be millions. And if I'm using a mobile phone, it should be scalable. I should be able to find a graph in a 10 million, node graph. I should be able to find a path, in a very large graph of, 10 million nodes in a way that doesn't drain my battery. Now, one interesting observation, and this sort of gets to the question before, how do I find this path? How do I find the path to Bob? So every implementation today does source routing. And in Eclair, I download the graph, I find the shortest path to Bob, and then I tell the next hop, this is where you should be going. Now, in academia, what they tend to focus on is per hop routing. And that's more like how the internet works today, where I give the job to the next hop, they know the final destination, and they've got to work out the next best hop that gets you towards that. So it's much more dynamic. Whereas source routing, if I say Olive's Bob, Dave, and Caroline, and Dave's offline, then it has to roll back.
But that's a greedy approach, right?
Oh, what?
That's a greedy approach.
The greedy, I don't know which one's more greedy.
Greedy, I mean the algorithm is like greedy.
Oh, you mean simple, like
For every step, you just observe what's the best next step, and you take that step.
yeah, that'd be per hop routing.
It's going to be the optimal route, right?
Well, actually, so this is actually this is actually a really interesting problem in routing. So there's 3 properties we care about. One, you would like to have a short path. You want a fast payment. The second one are the fees. You want a cheap route. But at the same time, you also want privacy. So there's this really interesting attack on Lightning where every payment on the network on average has 3 hops. And if you send me a coin, you're only 3 hops away. So I look at the graph from whatever node I received it from, and now I know you're within one of these nodes. So now you're no longer hidden amongst 10 million nodes. You're only 3 hops away, so maybe it's only 20 nodes. And I can start to work out who's sending coins to who. So if you want privacy, you want a long route. On average of every route is like 12 hops. And the graph's bigger, your anonymity set's bigger. But then it may cost more money, and it may take longer. So the latency. So it's really hard to say what are we optimizing for. Right now they just optimize for shortest path because it's easy. Long term they'll probably optimize for fees or privacy. Yeah.
What information do you disclose when you have a node, when you run a node or make a payment?
So there's 2 different settings. One's like a private channel. I have a channel of a hub, and I don't advertise anything. The hub will I give the hub the route, and they route it for me. Or if I'm a hub or a peer in the network, then I advertise all my stuff. I don't advertise my current balance. I just advertise my capacity. I say, this is a channel of 2 coins. Now you could probe that, and I think there's some attacks around there that probably aren't disclosed yet. But you could probably probe channels on the network to work out how much coins they have in real time.
But you know their maximum capacity.
Yeah, you know their maximum capacity, yeah. Okay. So if I want to send a payment, that's actually another thing they optimize for is, so a lot of these channels have small capacities, let's say $100. So if I want to send $10,000, what I need to do is set up 10 different paths to the same destination, and now I want all the paths to execute at exactly the same time. So that's called AMP. Atomic multipath payments, where I find 10 or 100 different paths, and it's only executed if all the paths are successfully set up. So there you're optimizing for value transfer. What are the channels, what's the paths with the most capacity? So there's still a lot of work to be done around that to understand what you're really working for. Yep.
For source routing, how often does the node has to compute the best path?
What was it, sorry?
For source routing, so
I mean, you typically do source routing when you want to send a payment.
sorry,
When you want to do a payment. So in Eclair, you download the graph in advance, then you compute the path when you want to send to someone. Yeah, so you just do paths on demand. Yeah. I don't know how real time that information is though. I don't know if Eclair feeds information in real time or just a startup. But yeah, you have the graph on your phone. There's also 2 other things you want to optimize for if you're designing these routing algorithms. First, I want to be able to find a path on the network without revealing how much I'm sending. If I'm sending 10 coins, I don't want to probe random nodes and tell them how much I'm sending. I want to be able to look at the path and say, this can probably do my payment. Then another one is transfer privacy, which we sort of hinted at. You know, if the coins are going from Alice to Bob, Bob, Caroline, Caroline, Dave, Caroline should have no idea who is the original sender and who is the receiver. You know, according to Caroline, it should just be a packet going through. She should really have no idea where this is going or where it came from. They're the sort of properties we're trying to optimize for. Go ahead. Oh, any other questions? Cool.
What is your incentive to open to have a node?
To run a node, so it's like a routing marketplace, so really you collect fees. At some point, people will pay fees for routing, and you make money for that. It's a bit like staking. You know, I'm staking coins in the network, and the more payments I facilitate, the more money I get. So that's actually what gets me excited by it. I normally talk about it at the end. You know, Lightning's actually a truly peer-to-peer network. Anyone can, run a routing node, and if you're running a routing node, your incentive is to find missing links in the graph and connect them. You connect that missing link, you collect the fees for that link. Yep.
Is it similar to how Tor networks are working? Or like
So what they've copied parts of Tor. So between Alice, Bob, Caroline, and Dave, they're doing onion routing there. They've implemented Sphinx, which I think is also in Tor. But there's two different. So a lot of the assumptions they make for that protocol for Tor don't always apply for Lightning. So there's still, but it's similar goal to Tor. Yep.
So could the routing payments, can they be part of the same kind of layer, same kind of packet as the transaction payment itself, or does it need like a separate?
No, the fees part of the fees are part of the payment. So what happens is that Alice will send 1.1 coin to Bob. Bob will take that 0.1 and then send 1 coin to Caroline. So you take your fee as you pass it along. And as long as the final hop accepts it, then everyone gets the coins. They all get a chunk of the fee.
So you need to negotiate a routing payment before sending
Yeah.
each hop.
Yeah, so normally a node should advertise what fee they're doing. And actually what's interesting is that if Bob's channel with Caroline, let's just say it becomes unbalanced. So Bob has 0 coins and Caroline has 1 coin. Maybe they'll charge a negative fee just to rebalance the channel. So then payments can start going this direction again. So there's a lot of, go ahead.
So if you have to negotiate the payments before each hop, then you have to do
So I think in practice they don't do any negotiation. I think what they do in practice is just they look up the fees and they just send it. Because right now no one's really paying that much. Like the fees aren't high.
Yeah, and if you send a transaction with a fee and then it doesn't work, you set your money back.
Yeah, it's just, right now the software automatically refunded and then you just send it to another path. And that's actually why I think Lightning is really promising for being censorship resistant. I would actually argue it's more censorship resistant than Bitcoin itself. Because in Bitcoin you have miners who can, they all go to the pub together and 7 of them showed up as scaling Bitcoin 2015 or 16 and they represent 80% of the network's hash rate. That's not decentralized. But here, you could have, potentially thousands or millions of peers all running this node at home, facilitating payments that ideally no one should be able to detect.
But if that's the case, if you have like, let's say, 2 million nodes, right? The fees, they're going to compete with each other for routing payments. So they're going to drop the fees. So the fees at some point might drop so much that it's not worth to run the node.
Yeah, I mean,
like less nodes, so like
it should balance out. It should find some market price.
yeah. So at some point you might have like 1,000 nodes, right? Because it's not profitable. To
Potentially.
more nodes in there.
Yeah, I don't think you need. I think if you have 1,000 peer-to-peer nodes in the network that have decent connections, I would probably argue today that's more censorship resistant than Bitcoin. Obviously Bitcoin's the base layer, so opening and closing channels are an issue. But if there's 1,000 peers, you've got to go find those peers, and there's just like random people. So that's why I'm really excited for Lightning, just because it's actually truly peer-to-peer. Any other? Yeah. Sorry.
Same question really, like, so would it be possible with the current system where the fees come off the top of the transaction, would it be possible to make the intermediary fees conditional on the transaction getting to Dave?
So right now they're all conditional. So right now if Dave doesn't accept, no one gets paid. So that's actually one of the issues. without a side channel. So,
Well, how does that happen if the payments are part of the same lump?
so what happens here is that when you send the payment, you include the fee and everyone takes their cut. Now, if Dave never accepts the payment, everything rolls back. So then there's no payment, there's no fees. So you only get paid the fee if the payment's successful. Like, there's no upfront fee for sending something. But now they're considering changing that because it's a spam vector. Someone actually recently built like a WhatsApp on this, where I send coins in Lightning, but then you don't finish the payment. So then you don't pay for it. It's actually one of the Lightning Labs developers. Okay.
That lock up funds.
It does, yeah, locked out funds, yeah, they send the coins, then refunds it. They abused the network, both. I thought it was funny because it demonstrates one of these big vulnerabilities, but it was also a bit annoying how easy it was to do. You know, yeah.
But then some issues by miners making this, like.
That's also an issue. If Lightning picks up, there'll be less throughput on the main chain. But I mean, if Lightning's picking up, though, there's going to be more channel openings. So it'll just be a different use case for the blockchain. Yeah, so I'm not too worried about that. You know, people are actually using Lightning, you're going to get a lot more channels. Okay, I'll move on anyway, just because of time. So that's channel-based networks in a nutshell. I think everyone got the rough idea what's going on here. If you didn't fully understand it, that's fine. Remember, this is 10 years of work that just got explained in an hour. So I hope this is a good starting point where you could go look at the resources online and you have a rough idea what's going on. Now I want to talk about our commit chains. But before I get to commit chains, I'll talk about payment channel hubs. Okay? So we have this non-custodial operator and they have this big pot of money. Okay? So Alice opens a channel with the hub. The hub will get some of his money and allocate it to a channel with Alice. As you can see here, the operator can send 2 coins to Alice, but Alice can't send any coins to the operator. Okay? So it's like a normal channel. Operator has 2, Alice has 0. And then let's say Bob comes along, and this channel has 4 coins. 2 from the operator and 2 from Bob. And then we have Caroline. Operator doesn't like Caroline, so Caroline deposits 1 coin, but the operator doesn't put any coins in whatsoever. And then of course, the operator really likes Dave, so operator puts in 4 coins for Dave, and Dave doesn't deposit any coins. So this is what payment channel hubs would look like if you use like Bitrefill or even Eclair. This is effectively what they're doing on their side when they open a channel with you. So let's have a deeper look at this scenario. Caroline has a channel with the operator, but Caroline can only send coins. She can't receive any coins. Caroline has to send the coin to the operator before she can receive any coins. Now in Alice's case with the operator, Alice can receive up to 2 coins, but she can't send any coins until she's received 2 coins from the operator. What's more annoying is that the hub needs to have a large deposit, and they need to consider how do they allocate coins to every channel, because there's an opportunity cost. If I lock coins in with Bob, and Bob doesn't do anything for 2 weeks, I've lost potential revenue I could have made with that money on a more popular channel. So you actually typically pay the privilege to open a channel with a hub. So these are some of the prices Bitrefill advertised at one point. So now you're paying for the privilege up front to open a channel with a hub. And there's risk. These coins are now live in a hot wallet. They're no longer on a piece of paper, in a safe or whatever, or wherever they keep their pieces of paper for their cold storage. They're now on your server and they're at risk. I mean, less risky than just running a normal hot wallet, but there's still some risk involved. And there's also an on-chain transaction to join, because every customer has a pairwise channel with the hub. So if a hub has 1 million customers, that's 1 million transactions. So that's more traffic, as I mentioned. If this gets popular, there will be traffic. So payment channel hubs are great for instant finality and no trust. The moment the hub sends these coins to Alice doesn't have to trust the hub whatsoever. So you can immediately redeem the coins on the blockchain and go her separate ways. But the collateral lockup doesn't make it permissionless. You need a good pot of money if you want to run an effective payment channel hub. And a lot of people lack the collateral to do that. So the question is, can we do better? Can we still have this central hub whose only job is to facilitate transactions between all of their customers? But can we do this with a weaker trust assumption? Instead of instant finality or instant redeemability, can we add in eventual finality? So maybe Alice sends coins to Bob via the hub, but they're not confirmed right away. They're confirmed, let's say, within 10, 20 blocks. So can we do better? And this is what a commit chain is all about. Okay? So you have this non-custodial operator whose only job is to collect off-chain transactions and post little checkpoints to the blockchain. Now, that's an example of a checkpoint. A checkpoint is basically the hash of a block. And inside this block, you have the state of the ledger, which is everyone's balance, and then you have the list of transactions. So it actually just looks like a Bitcoin block or an Ethereum block. Okay, so Alice comes along, and Alice will deposit one coin into the operator's commit chain. Now Alice can send this one coin to Bob. Alice will sign it, give it to the operator, and the operator will forward this on to Bob and say, Bob, you received one coin from Alice. But this transfer isn't confirmed yet. Okay? It's just that the operator has a copy of it. And now we wait around. The transaction is pending. Eventually, the operator will post a checkpoint. And the checkpoint will confirm Alice's transfer. Because after all a checkpoint is a list of transactions and a ledger state. And that transaction will be Alice's transfer to Bob. And then we just keep doing this. The operator keeps listening for off-chain transfers. They post these little checkpoints to the blockchain, and they keep confirming these transactions over time. Now, what does it mean to be secure for a commit chain? Well, first, if Alice has one coin on the service, then only Alice can authorize the spend. The operator shouldn't be able to just run away with the money if Alice deposits coins. And then there should be this thing called balance security, just like channels. If this operator disappears, Bob has enough evidence to send to the blockchain and withdraw their money out of the service. And of course, now we have this new requirement. These little checkpoints are getting posted to the blockchain periodically. How do we make sure that's valid? How does the blockchain, like an Ethereum smart contract, how does it verify that this block is valid? It doesn't have the computational resources to verify every transaction. So how do we make sure that is valid? So that's what we're going to cover now. Okay? So hopefully this won't be too long, because I know everyone's quite tired on I don't even know what day it is now. Is it Wednesday? Wednesday night. So these checkpoints, there's two different ways to design them. Okay? One is more like a potential claim. So it's just like a Merkle tree. It's an account-based one. There's a list of accounts. You build up your Merkle tree. You get the root, and you just post the root of the tree on the blockchain. You're just posting a little hash, and that represents a commitment to everyone's balance. Now, what's important here is that they're potential claims. So on the commit chain, it will say that I have one coin. And on the blockchain, there's this big pot of money. Now, I have a potential claim to one of those coins. So if I can issue my withdrawal, I'll get any of the one coin. I'll get one of any of the coins. Now, there's a problem there. If something goes wrong, and this big pot of money loses money for whatever reason, let's say there's a malicious withdrawal, and one person gets away with a coin. Now there's 99 coins, and there's 100 potential claims. If there's 100 potential claims to a pot of 99 coins, one person will lose out, and they'll not be able to get their coin. Okay? So that's sort of how they're being designed at the moment. The other way, and this is more like plasma cash, in this tree of this ledger, every account is assigned a coin. So every coin has a unique serial number. So if a coin gets stolen from the big pot of money, we can actually say who lost that coin. So maybe Bob lost the coin, because Bob's coin was stolen because Bob didn't watch out for it. So it's no longer a potential claim, it's a fixed claim. I know exactly what coins belong to me. I know exactly which coins I have to defend if someone tries to steal them. Okay? So what if an invalid withdrawal is successful, as a terrible typo, is processed? So I should have hinted at this. In the potential claim case, if one coin is stolen, then everyone has to withdraw immediately. If you're the last person to withdraw, you don't get your one coin because that doesn't exist in the pot anymore. In the fixed claim world, it's a local impact. If Bob's coin's stolen, only Bob is impacted and no one else. Okay? So if that sort of doesn't make sense right now, don't worry about it. You know, just come back to this at a later date. I think most people in the rollup world still don't understand this themselves.
How could an invalid withdrawal be processed?
We'll see now.
Okay.
I'll get to that. Yeah. Because in the community, they always mix up account-based and UTXO. And what they really mean is potential claim and fixed claim. For them, this is accounts, this is UTXO. But actually, that's not really the problem. It's more about how do you assign claim to a coin. Just in case you ever see people talk about that. So what are the fundamental problems emerging for these checkpoints? Okay, so a checkpoint, as I mentioned, is just a hash of the ledger and the transaction list. Now, the first problem is, what if the operator poses a checkpoint and they don't make the off-chain data available? So every time I post a checkpoint, I should tell you your new balance. I should say, here's a checkpoint, and here's enough information for you to withdraw your money. No, you provide let's just say you own this coin. If you own this one, when I post this checkpoint, I should give you that branch. I should say, here's the evidence you need. If I disappear, post the evidence and you can prove you own this coin. Now, what if the operator doesn't do that? What do you do about it? There's a checkpoint, but I can't prove to the blockchain that I own a coin. So we'll get to that, how the solutions for that. Another one is integrity. What if the checkpoint is the hash that says Paddy is cool? That's a valid hash. How does the blockchain verify that the checkpoint is meaningful and isn't just like a hash of a random word or phrase? And why do these problems even exist? So the problems exist because when you think of a new blockchain protocol, when you think of sharding, when you think of sidechains, you always assume the verifier, you and I. We have the computational resources to verify every transaction, and we can store everything. You know, we can store all the transactions. You give me a block, I store it, I validate it, it's correct. Now in the commit chain world, the verifier who enforces the rules is a smart contract. The smart contract doesn't have the computational resources. You know, it's a really dumb contract. Nor does it have the storage. If you're processing 1 million transactions off-chain, you can't send that to the blockchain. So how do we make sure the verifier can get, you know, the checkpoint and enforce that it's correct? So what we rely on are these third-party observers, you and I. We observe it. And if we find any problems, we tell the smart contract about it. So we just move the problem from the smart contract to third-party observers. So let's see how we do that. Is there any questions at this point, by the way? This is quite abstract. You're like, yeah, it's very abstract. Yeah. So this is why it's a deep dive. Okay, so let's see how we solve some of these problems. So for checkpoint integrity, okay, so the first approach is a fraud proof. Okay? So here, the checkpoint has been posted. Yeah, the checkpoint's been posted, but it's invalid. What any user can do is issue and challenge. So let's just say I'm the operator, I post a checkpoint, but I don't tell you your balance on the checkpoint. You know, I don't give you that Merkle tree branch. I don't give you enough evidence to prove to anyone what your balance is. You could issue a challenge and say, operator, you have to reveal this on the blockchain. You have to reveal the evidence that I need to withdraw my coins. If the operator doesn't do that by the challenge period, then what it will do is invalidate this checkpoint, roll back, and shut down the entire service. So that's a fraud proof. Okay, you issue the checkpoint, but the checkpoint is not confirmed until after this challenge period. That in this case could be 72 hours. After 72 hours, the next checkpoint gets in, and this is just considered valid. It is assumed as valid if no one's tried to challenge it. Is that clear? Any questions for that? Cool. So as the operator, I post checkpoints. If nobody challenges this checkpoint within 72 hours, it's just considered confirmed. And the blockchain will assume all the data is available, the ledger's correct, and all the transactions are correct. Okay? And it's the same for withdrawals. So in this example here, what I could say is I want to withdraw this coin from this previous checkpoint. But maybe there's been 100 checkpoints since then. Maybe I got this 3 months ago. I never spent the coin, but 3 months has passed, and now I want to withdraw the coin. So what I could do is issue this branch and say, I owned, what was this? I owned 1 coin at this checkpoint. And now there's a challenge period. If nobody can prove that was spent, then the contract will eventually give me the money. And that's exactly the problem that I mentioned earlier. What if I withdraw a coin that's already spent and nobody provides proof of that? If I get through that challenge period, I've sent you the coin, but then I try to withdraw it, and you don't prove it's already spent, then I steal your coin. Okay? So that's the idea going on there. Now that is to solve checkpoint integrity, to make sure this is valid and all the withdrawals are valid. But it's a bit awkward and a bit annoying. Because now the user has to be online. We have to be online to check every checkpoint. We have to be online to make sure people aren't stealing my money. And I have to be online to make sure all the data is available and I always have evidence to withdraw my coins. And that's a huge burden for the user. So can we solve this problem? Can we remove some of these liveness requirements? So this is what I just mentioned before about the fraud proofs. So I'll just skip this section for now. Okay, the idea is that a checkpoint's posted. I can issue a fraud proof, and then they're non-interactive. Yeah, I'll just skip these for now. Okay, so I mentioned about the fraud proof idea. But what you could do instead is, let's just say I send a checkpoint. What if I issue a zero knowledge proof? I've got the wizards here. I don't know if you recognize any of them. Two of them are London-based. Can I prove the checkpoint's valid using a zero knowledge proof? And that's basically what you're doing. So what I can do is I can issue the checkpoint on a zero knowledge proof that the checkpoint is well formed and everything's correct, without revealing the transactions itself. So it's a very simple idea. I post checkpoint and proof, and that will convince the smart contract that is correct. Because all snarks are used for is verifiable computing, and that's basically what you're doing there. But that only solves one problem. It only solves checkpoint integrity. So now we don't need these fraud proofs anymore. This is basically the problem here. I don't need to wait around. So without zero knowledge proofs, you put a checkpoint and you have to wait 72 hours before it's confirmed. Because what you're really waiting for is for someone to prove that it's invalid, to send a fraud proof. So you can replace fraud proofs with zero knowledge proofs. You can just prove that it's valid using this magic wizardry, and we're all happy. Now, what I do want to highlight is that this is only one tool in an engineer's toolbox. So this is a quote from Roger Needham that says, if you think cryptography will solve your problem, you either don't understand cryptography or you don't understand your problem. Because a lot of people say, throw a ZKP at it and it solves everything. And it doesn't. It solves this one small problem. What's even more problematic is that proving that a checkpoint is valid takes time. It's quite slow. It's a lot of work to be done there to make it more efficient. And verifying the proof on chain isn't cheap either. It's only been, before, when I gave this talk in November, it would cost 500k gas to verify a snark. Now it's 100k gas. So the prices are going down. A little bit artificially. But it's still expensive. A fraud proof is just a hash. I just send the hash, and that's all I need to do for every checkpoint. Here, I need to send a proof. There's also moon math. There's very few people in the world could explain to you how that works. So it's not really verifiable if no one here can actually understand how the ZKP works. Okay? Now you would think, well, if I can post these checkpoints out rapidly, checkpoint proof, checkpoint proof, checkpoint proof, can I do that now? Do we need this challenge period anymore? And actually that really comes down to how do we solve withdrawal integrity and data availability. So let's go to the data availability problem. So just to highlight the problem, I post a checkpoint, but I don't make the data available. You've done 1,000 payments with Alice. I confirm your transactions in a checkpoint, but I don't give you that off-chain data. I don't give you enough evidence to prove that you have coins according to the checkpoint. Is there any way we can force the operator to do that? Okay? So the first approach is the easy approach. You just wait for data availability, and you don't consider the transfer confirmed until you get the data. So you can imagine the checkpoint gets in, and then the operator gives Bob the data. If we only consider confirmed when I get the data, that's one approach. If you don't get the data, well, it's not confirmed. So that's what they were doing in Plasma Cash. And that only really works if every coin is associated with an owner. That fixed claim approach that I mentioned. It doesn't really work for the general case. This is a bit annoying. Another one is on-chain challenges. So the checkpoint gets in, and again, you wait 72 hours, and I could issue a data availability challenge. So operator posts a checkpoint, doesn't give me the data. I issue a challenge on the blockchain, and they have to give me the data on the blockchain. If they don't give me the data, then this would be invalidated, and we roll back to the previous checkpoint, where we assume the data was available. But that's annoying, because now you've just reintroduced this 72-hour challenge period, which was the whole point of zero-knowledge proofs to get rid of. So you're now stuck with these challenges again, so no one really likes that. Or, this is the Starkware proposal, you could have a watchtower committee. The non-custodial operator sends it over to the watchtowers, and they all sign off on the checkpoint. They say, yep, I got the data, I got the checkpoint, I sign off on it. Then the little happy smile goes to the blockchain. So now the smart contract is convinced that a third-party committee has the data and can make it available. But then this brings up the question, if you have this third-party committee, why do you need the blockchain? Why don't you just trust them to run the protocol? Because that's basically a consensus protocol. So it does solve the problem, but not really, Sort of walks around the problem a bit. So there's 3 different ways we've thought about solving it. You wait for the data, you issue challenges, or you outsource it to a committee. But none of these are really great solutions. So why don't we just post all the data to the blockchain? That's one way to solve it. And that's rollup. Rollup is a commit chain, but the data is posted to the blockchain. So as a stronger assumption, it assumes the verifier can store everything. Maybe they can't validate every transaction, but it can store every transaction. So it's not really off-chain. It's layer 2. You have an operator collecting the data, and they post it, but everything's on-chain. So it's not really off-chain. Okay? And also, it also comes down to so while we can post everything on-chain, it still doesn't solve withdrawal integrity. How can I make sure I can always get my coins out? The 2 approaches they propose is the on-chain challenge, and you reintroduce that challenge period, or you rely on one honest party in the consensus protocol, which is sort of getting around the problem. Okay, and this is like a summary of some of the protocols. Okay, so you have no cust, that's like liquidity network in London. You have some of the plasma caches. You have rollup with ZKPs, and you have optimistic rollup with fraud proofs. And you can see that they're all very related. And what's nice is that the rollups are getting popular now because the data availability problem was a pain in the ass, no one thought of a good solution. You just post everything to the blockchain. By using a zero-knowledge proof, I can post the data, I can post the proof, I can post the checkpoint, and I can prove to everyone that all the transactions are valid. Yep.
I just don't understand how you post all the data to the chain. I mean,
Oh, yeah, so why do they do that? So actually what they're posting is a compressed version of the transaction. So what you'll really have is the sender, receiver, and the value. So it's not all the metadata. And actually, if you use zero-knowledge proofs, you don't actually have to post a signature. Because actually in the proof, you can prove that all the transactions are valid and they were all authorized and signed. So all you post is the data. You don't actually have to post signatures. So it's more like compression. I don't like saying compression because that involves encoding. You just post less information. So I think the minimum they've achieved now is 900 gas per transaction. Which for an Ethereum transaction, normally 21,000 gas, it's a much better use of the network. The main bottleneck to scaling becomes how fast can I send this information across as opposed to how fast can I validate the transactions. So validation isn't the bottleneck anymore. It's more information propagation. Yeah.
So on the checkpoints with a challenge period, why does it need to be a challenge period, and why, rather than why couldn't they just stake for it?
I mean, even for staking. So do you mean does this slide? Where is it? Don't know what I did with it now. Do you mean like this? So there's two problems. One is how do you guarantee this is valid? And the second problem is how do you guarantee the data for this is available? So the only way we can guarantee this, let's ignore zero-knowledge proofs for now. If I post a checkpoint, you need some challenge period so anyone has an opportunity to prove it's invalid.
But
yep.
Rather than having a timed challenge period, why couldn't you challenge either of those things way after 72 hours, assuming that the
yeah.
the checkpoint operator is still in business and still has a
Yeah.
stake?
So there's two things I can mention. So the first one is that for commit chains, the main problem is the data. And what you really want is this to be confirmed and it can never be reversed. So what could happen is that if data availability is an issue, anyone could post that challenge at any time. And if anyone can post that challenge at any time, I could post it for a block 6 months ago. And if that gets invalidated, does that mean we have to invalidate all future checkpoints? So really you want to be able to say, here's a checkpoint and it's confirmed. We'll never roll back past this point. So the way to achieve that is you say, after 72 hours, this is confirmed and we'll always roll back to this. So we have to assume it's correct. And that's mostly because of data availability. Now what is nice with rollup here, so I'll just go the optimistic rollup. What's nice about optimistic rollup is that the checkpoint gets in and all of the data. And it relies on fraud proofs. But all the data is available. So as a user, you get the checkpoint, you get the data, you validate it yourself, and you know it's valid. And there cannot be any more challenges that would ever make this roll back. Because you validated it, all the state transitions are correct, all the transactions are correct. There can never be a successful challenge for that block.
And all the previous.
And all the previous ones. Yep, you start from the start, go the whole way up, and you can always convince yourself that will never be rolled back. And that's really nice, because data availability is no longer a problem. Where data availability, you have no guarantee if the operator gave everyone the data. Maybe he gave you the data, but not someone else. So it's asymmetrical information. So that's I'd hope that answered it a bit. Yep.
So for simple transactions, this seems to make sense. But what about
Smart contracts.
Exactly.
So smart contracts are trickier. So optimistic rollups probably easier for that. Because for smart contracts, what you're really doing is just posting you're posting the transaction, and then everyone else is validating that. So what you're really doing is pushing the validation problem from the miners to the users. Miners don't validate anything. They just include it, and then the user can prove it's invalid. So what's nice about that approach is that the smart contract just has to be designed to support fraud proofs. I mean, not even the smart contract, just the rollup. So I read a smart contract, I put it on rollup, and the rollup framework will then enable the fraud proof for me if someone can prove that a single state transition from a transaction was invalid. So what you do is that there's 100 transactions, maybe the 50th transaction's invalid. So you just tell the blockchain, re-execute transaction 50. The blockchain will re-execute it, discover it's invalid, and then just remove that state transition.
Right. So that's,
Yeah.
I think, if a smart contract is operating sort of on the rollup.
Yeah.
But what if I am operating on the rollup and I want to interact with a smart contract which is on main chain or is on a different rollup? How, the smart contract can't independently read from these proofs.
Yeah, so this becomes like a sharding problem. So rollup is more like sharding, where you have two independent chains, and now you're basically saying, how can this smart contract talk to another smart contract on another blockchain? So you need to have some cross-chain communication protocol there. So now what we actually end up with is we have the off-chain world with channels, we have the sharding world, and now they're mixing together here with rollups. Because it's just a shard. The only difference is that it's all encapsulated in a single blockchain, as opposed to different blockchains. So it becomes more like a sharding problem. I think that sort of answered it. Any other questions, or should I continue? Because I know we're running out of time. Cool, I'm nearly done. So basically what's important is that what a lot of people miss in these designs are the user liveness requirements. Should the user have to watch out for other users stealing their coins? We witnessed that with the fraud proofs. Should the user be responsible for holding the hub accountable? If the hub doesn't reveal the data, is it up to me to issue that fraud proof? Should it be the other way around? And finally, should the hub be responsible for responding to on-chain challenges? What if I have 1,000 users who issue 1,000 challenges? And I have to respond to all 1,000 within a time period. That could be a DOS factor for the hub. And we don't really have good answers for this yet either. Rollup is the one most people are excited about because it solves the data availability problem. And it's more easy to think about and reason about. And this is a slide I made. This is actually mostly incorrect now. A lot of it is outdated because I made this 6 months ago. 6 months later, everything's different. But what I mostly highlight here is the fraud proof approach is the cheapest. All we post is a hash. With snarks, there's 100K gas now, so maybe more like 150K gas. Starks, they actually hit, after you do 10,000 transactions, you hit the block limit. So Starks grow based on the size of the thing you're proving. In this case, the number of transactions. And ZK rollup at the time would achieve 9K transactions. Because you have to post all the data on the blockchain. So every time there's a new transaction, there's a linear increase for rollup. So if you're an operator, what would you choose? This is your cheapest option. These, get more expensive over time. If you're an operator and you trust you're not going to treat your users, if you trust you're not going to cheat your users, you're going to go for the cheap option. If you're a user, you probably want the operator to use the expensive option because you don't trust the operator. So if you're going to run this service yourself, which one are you going to pick? And it's going to really come down to cost and the trust relationship between you and your users. But I'm going to finish with this slide, which is nice, just on time. What I believe in the future is that most services on the internet will be built using commit chains. Why? They're self-custody. Once that checkpoint gets in and it's confirmed, I no longer have to trust the operator. I only trust the operator from the time I issue the transaction until it gets in the checkpoint, and that checkpoint gets confirmed. So now we can prioritize the self-custody of users. And there's a lock-in effect. I have to lock my coins in a commit chain. And this could be locked in for a day or two. So it's really difficult for users that migrate from a commit chain to commit chain. So as an exchange, I built my moat because I have, let's say 10,000 users locked in and they're all locked in for a day. It's time consuming for them to change. And really when you think about it, this is just batch confirmation. I have a database, I process 10 million transactions, I'm doing one big batch update to the network using a single hash or rollup. And actually I outsource liability. You know, as an operator, I no longer have the whole custody of any of my customers' coins. You lock coins into me, but I never have custody of it. So I no longer have to worry about protecting $2 billion worth of tokens. I outsource that liability to the users. But what commit chain design you will choose will depend on the ongoing financial cost, the hub's appetite for risk that the service can hold, speed of confirmation, speed of withdrawals, trusted setup, you know, do we want to use a snark or a stark, and if you need a watching service or not. And this is the trust but verify feature. We still trust the operator. We trust that they will not censor our transactions, but that's it. I can always withdraw my coins if I detect any malicious behavior. And actually, you can also set it up where if they censor my transaction, I could penalize them and make them lose money. You know, they give me a signed receipt, they promise it will be in the next checkpoint. If it's not, I give the receipt to the blockchain will then slosh their deposit. You know, we can actually add some financial accountability in there.
That's a bit contradictory, right? Like
Yeah.
if you verify, you don't trust.
No, so so it's like a white box algorithm in a sense. You know, you're running something. I can verify everything you're doing. I constrain your ability. But there's still some things I trust. That you're online. That you create blocks. That you do stuff. But you can't do anything except for that. You know, you can't create an invalid transaction because I verify everything you do. So there's still some trust. It's just we constrain that trust to a small set of actions that you can do. And those actions shouldn't be able to harm me. So it's like a Ronald Reagan quote as well from the Cold War. Now I just want to skip to the end. We don't really need to talk about watchtowers here. See, I have too many slides. Okay, cool.
Good question.
Yeah.
Did you make the slides available?
Yeah, I'll post them on the Eventbrite if you want. So one thing I want to highlight is, just as we finish, what I see coming up in the future, this would be my dream. We'll have this peer-to-peer routing network. Anyone can run a node, anyone can stake coins, and anyone can facilitate payments on the network. But as I mentioned, something like Lightning isn't good for payments, but it excels as a routing network. Then we're going to have these non-custodial hubs. Today, they're payment channel hubs. That's the best that we can do. And hopefully at some point, they could be commit chains. It could be like a WordPress plugin you install. You install it, you now have a commit chain. No collateral lockup, anyone can run that. And you may or may not need this watching network. If it's rollup, you don't need it. If there's fraud proofs involved, you'll need some watching network. And of course, the blockchain then becomes the settlement system or root of trust for all of this layer 2. And if that happens, that's really exciting. And obviously, there's a bunch of companies building this, so I normally put this up. You know, you have like Starkware, Liquidity Network, Plasma Group. You have all these channel companies in the middle, and they're building up these systems. So this is coming. It's just probably, I think to the full extent, we're probably still 5 to 10 years away. But now we're starting to see the seeds growing and these, you know, applications develop. So that's the end of the talk, I guess. I hope everyone's not too tired after that. I was hoping to get a break in between. Cool. Cool. So I don't know if we have to leave now, but I can hang around for a few minutes if people want to chat and just, I don't know, talk about Lightning. Cool. Thank you, guys.